right. Good afternoon, everyone. Thank you so much for joining our webinar on EV battery strategy, where we'll try to help you answer the question of whether sodium-ion will disrupt LFP in EVs before 2030. My name is Jard van Ingen. I'm the CEO and co-founder here at GetFocus. I'm joined today by Martina.
Hi everyone, thank you for joining. I'm Martina. I'm on the sales team and we're excited to show you our findings. So to get started, we will give you a little bit of context on how we conduct our analysis, and then Jard will take you through the actual insights and the results. The reason why we built GetFocus and our methodology to assess technologies is because when we talk to those whose responsibilities is to make this high-stake decision when it comes to technologies, like people in R&D, innovation or strategy, they all tell us the same thing, which is that ultimately you're judged on how the company performs tomorrow, so on the future, but most of your day is consumed by the present. So you're worried about the tasks, the team, the organization, and positioning the business for tomorrow is the most consequential responsibility, but somehow it always gets the least amount of resources and time. And unfortunately, it will only get worse, because if we look empirically at the number of emerging technologies that are out there to keep up with, it grows exponentially every year. Today, we already have over 265,000 domains of technology. So by the time you map your landscape, it's already moved. And that's why you need a system to keep track of everything rather than just a snapshot. And here's what happens if things go wrong, and you are familiar with most of these. If we look, for example, at the Kodak case, they literally invented the digital camera, but then they went bankrupt to try to defend the film technology. Or Nokia, for example, at the time it was, it's a similar story, because at the time it was the leader of the mobile space, but then they missed the shift to smartphones. But this also happens at an industry level and not only in our organization level. So if we look at the automotive, for example, and the battle between fuel cells and batteries, we know that billions of dollars have been burnt on pursuing fuel cells, but in the end batteries took the cake. So it's interesting to notice that disruption keeps happening over and over. And the striking thing is that in every single of these cases, what these companies and the industries bet on seemed like the sensible choice, because that's where the consensus was, but yet the data said differently from the very beginning. And that is exactly what we do differently. So trends, conferences, or consultants, what they do typically is count activity in a given space and for given technologies. But that's what we don't do. We don't count, because we measure. Specifically, we measure the only signal that can actually reveal which technology will win before it becomes obvious. So you still have time to respond. So the question becomes, why not look at today's performance as a good indicator of where technologies will go? Because performance today tells you how things look today. But MIT, for example, has been studying technological developments for decades, and what they found is that all the technologies improve exponentially. But here's the tricky thing with exponentials. So if we imagine a challenger, so the line in blue, that it's improving at a higher rate than the incumbent, it will look for a very long time like it will never catch up. So it often gets ignored until at some point it shoots right past it. And that's exactly why disruption feels like it's coming out of nowhere. It actually doesn't. It's just that if you know the rate beforehand at which these technologies are improving, you can actually see it coming before it happens. And that's not just us telling you, it's over 30 years of MIT research, and what they started with was a very simple question. They asked, can we objectively measure how fast technologies improve? So what they did was selecting 28 technological domains, and they measured year by year real cost and performance for each of the technologies in that domain. So if we think, for example, of hard drive, then real cost and performance would be gigabytes per dollar, for example. And what they found was that every single technologies that they looked at improved exponentially and also remarkably consistent. So the rate of improvement stayed consistent year after year. So it's like every technology has its own more slow, just that some improve very fast and some slower. But the real breakthrough was realizing that when they looked at competing technologies, so technology that tried to solve the same problem or they had the same functions, it turned out that the one with the highest improvement rate, so the one that increased its performance and reduced its cost faster than the alternatives, has historically always been the one that takes over and become a dominant option or the new industry standards in a space. So for example, on the slides, we have LED lighting versus incandescence lighting. LED was improving at 34% per year, while incandescence at only 4%. And what do we see today? That almost everything is LED and incandescence is not seen anymore. So this was a very powerful insight. But the catch with their research and their method is that it can only be measured after the fact. So once the technology was already on the market, and they could actually empirically measure it. But this means that it was too late to really act on, because it took them 6 years to only collect all the data about those technologies. So it's too late if you want to use it strategically. So that's when we started to collaborate with them and try to find if there's a way to estimate the rate early without having to wait to measure it after. And turns out that it is possible. And the way we can do it is because we have found the leading indicator that correlates with the improvement rate of technology hiding in patent data, specifically in the citation of patent data. So what we do is that we scout global patent data to retrieve every single patent that relates to a given technologies for all the technologies that we are evaluating. And then we measure 2 key metrics in the citation network of patent data. The first one is called cycle time, which looks at how many years it takes for a new generation to build on the last. And this is basically a measure of how fast are the steps. And then we look at the second metric, which is knowledge flow, which is basically once we have a new generation of a technology, how much later work builds on it. And this is a measure of how big are the steps that the technology takes. And turns out that faster steps and bigger steps together correlates to a high improvement rate, and therefore a technology that improves fast. And we validated this method with all the MIT domains, the ones that they looked at, and we also expanded it to over 150 since the original research. And the insights that we are going to present to you, therefore, are not AI-generated prediction, but it's the forecasting is actually explainable and a peer-review method that we developed with MIT. But without further ado, I'll leave the floor to Jard that will actually show you what we found for the topic of today.
Right, so you might ask, what does any of this have to do with batteries? So basically what we did is for the question of whether sodium-ion can and will disrupt LFP in the same way that LFP disrupted NMC, is we took a very broad view at the landscape of emerging and incumbent battery technologies. Yes, for sure the slides will be shared. No problem. So basically we looked at every single emerging technology within batteries that we think is in the race to at least have a meaningful share of the market before 2030. So we've looked at sodium-ion, LFP, LMFP, M3P, NMC, NCA, high nickel, lithium-ion, various solid-state technologies. And we did so across the full battery stack. So for each of these chemistry options, we've looked at all the emerging anode technologies, cathode technologies, electrolytes, production techniques, full cell platforms, etc. So in total, we've created 254 data sets representing each field of technology individually. We've measured the cycle time of each, we've measured the knowledge flow, and we've come up with estimates of the rates of improvement of all of these different technologies, and that's what all the rest of the slides are based on. So when we have all of the improvement rates for all of the various competing technologies, what we do is we typically divide them into 4 quadrants, also utilizing the technology readiness level. So we find out for the technology what is its readiness level, we find out what is the improvement rate, and then based on that we develop a matrix that has 4 quadrants. The Act Now quadrant for mature technologies that are also improving fast, the phase-out quadrant for mature technologies that are not improving so fast, comparatively speaking, the ignore quadrant for immature tech that is also improving slowly, and then the watch closely quadrant for immature technologies that nevertheless have a very high rate of improvement. Then the executive summary, and then we'll go into much more detail in a little bit. So when we look at all of the technologies combined and we calculate an average, so across full cell, anode, cathode, electrolyte, etc., what we find is that sodium-ion has been improving faster than LFP and NMC since 2023, and that the gap is quite significant. That signal repeats itself across the full battery stack. So whether you look at the full cell platforms, at the cathodes, the anodes, the electrolytes, or the manufacturing techniques, in every single case, sodium-ion related technologies are improving faster than LFP or NMC, and in most cases also solid state. But what is slightly different this time is that LFP is different from what happened before with LFP versus NMC, because it is already very cheap, it's mature, safe, durable, still improving, and currently it's still significantly cheaper than sodium-ion. And our final base case conclusion is that there will be segmented competition before 2030, but our more aggressive interpretation is that we believe that by 2030 we will already start seeing meaningful disruption in LFP addressable segments today. Then, if we look at the historical full battery landscape improvement rates, what you can see here is 3 lines. So on the y-axis we have the improvement rate, on the x-axis we have the years. What you can see is that since 2010, for almost the whole time, sodium-ion has improved slower, but then something changed drastically in 2021, and since then we've seen an explosion in the rate of improvement. And since 2023, you can see that sodium-ion is now improving significantly faster than both LFP and NMC. And what is also interesting is that if you just compare LFP to NMC, you can see that since the early 2010s, LFP has also been improving faster than NMC. And what we see in the market now is that NMC is losing market share. LFP has very aggressively gained market share. And in this historical analysis, you can see that the change in improvement rate precedes the disruption or the displacement in the market. So we're foreseeing something similar in the case of sodium-ion. Then, what is different this time? So when LFP was or is disrupting NMC, the advantage for LFP was cost, safety, cycle life, and lower critical mineral exposure. The main weakness was lower energy density, and we found that the improvement rate preceded the adoption. Now with sodium-ion versus LFP or LMFP, what we see is the advantage for sodium-ion is, of course, the raw material abundance, independence from lithium, cold performance in particular, safety, and the possible cost floor, although today it is still more expensive than LFP. And again, main weakness is lower energy density. So high level, summarizing all of it together, we see that today the improvement rate for sodium ion is about 113%. For LFP, LMFP, M3P taken together, it's about 58%. And then NMC, NCA, NCMA, it's about 44%. So whereas we've seen increasing disruption of NMC by LFP based on a relatively minor difference in improvement rates, the difference in improvement rates this time compared to sodium ion is quite significant. So that also points at a likely more aggressive displacement than what we saw before. Here we show you the same information, but also plotted on our decision-making matrix, where you can see that both the technology readiness levels and the improvement rates are taken into consideration. And so the reason why we're not fully seeing this happen in the market yet is because sodium ion is still relatively immature compared to LFP and NMC. But its improvement rate puts it squarely in the fund or act now zone. So as we see it, it won't take long before you can really start seeing the effects in the markets. Then if we split it apart further, because within each of these categories there's many different underlying technologies. If you want to look at all of them in detail, we have the full report available for free on our website. But here we're just showing you some of the highlights. So if we look at the three fastest improving cathode technologies among everything that we've measured on the cathode side, the Prussian blue O3 layered oxide and P2 layered oxides are improving by far the fastest compared to every other cathode technology, whether you look at LFP, LMFP, M3P, NMC, solid state, etc. Sodium ion is improving much faster on the cathode side, and also its technology readiness levels are approaching full maturity. And in particular for the EV segment, the P2 layered oxides are interesting because of the energy density benefits that they bring. And also they are the fastest improving out of all of the cathode technologies that we looked at. Then on the anode side, what we find is that again the sodium ion anodes, all of which are made of hard carbon, are improving faster than all of the other anode technologies out there, and also significantly faster than graphite. But also silicon enhanced anodes. So again there we find that out of all the anode technologies, sodium ion related anodes are improving significantly faster than those associated with competing chemistries. Then the electrolytes, here the difference is not super meaningful. This, I would say, falls within a measurement error for liquid lithium-ion and solid electrolytes, and then the sodium-ion electrolytes. So the main disruptive innovation is not necessarily coming from the electrolyte side, more from the anode and cathode and full cell platform sides. But still, nevertheless, sodium-ion electrolytes are also improving marginally faster than those associated with competing chemistries. For Tim, I see you have a question for the polyanionic cathodes. If you go to the report on the website, you'll see in much more detail how we treat all of the various cathodes that we took in consideration. Then also when we look at the manufacturing technologies associated with battery technology spread across the different chemistries that we looked at, we see again that the technologies that are present there associated with sodium ion are improving faster than other technologies, with the exception of LFP recycling technology, which is improving slightly faster than even the sodium ion related technologies, but of course LFP recycling doesn't necessarily help the performance of LFP batteries themselves. It's more of an adjacent technology, but interesting finding nevertheless. So if we stack it up across the board, both the historical rate for sodium, the historical rate for sodium ion as a whole is higher than that of LFP, LMFP, and NMC. The full cell platforms improve faster than the other two. A cathode improves faster, anode improves faster, electrolyte marginally faster, and manufacturing technologies also faster. So what this tells us about the future is the following. So what I want to emphasize is that the rate of improvement will precede the actual improvements that you start seeing in products that will end up on the market. So currently, CATL's Naxtra cells reach up to 175 watt-hours per kilogram, which leads to about 400 kilometers of range. So, not as competitive as some of the other chemistries out there, and also on the cost side, it is still more expensive. So on the face of it, not very competitive, and unlikely that it will be competitive when you compare it to LFP or NMC. But the rate of improvement tells us that these things are improving significantly faster than the other two chemistries. So what looks like a big gap today will be an ever-shrinking gap, and before you know it, the gap will be crossed. Potentially not on energy density, because there's just a limit on how energy dense sodium ion can get, at least currently. But in terms of the performance per unit of cost, which is actually what the improvement rate is measuring and predicting, sodium ion is improving significantly faster. So we expect that the gap will shrink ever faster, and that has consequences also for what the posture should be. So really the question is not, is sodium ion going to beat the rest on energy density, because that also wasn't the case for LFP versus NMC, and is still not the case. The question is, when does it become good enough, and good and cheap enough? And what we're forecasting is that that's going to happen faster than people realize. So then again, this is a fairly conservative take of the 2030 battery stack for EVs. So we think still the premium long range will be dominated by NMC, NCA. Mainstream will, to a large extent, still be populated with LFP and LMFP, but we do think that already there sodium ion will start showing signs of disruption. And for the low-cost, cold-weather, short-range segment, sodium ion will become a very serious competitor to LFP by 2030. And then longer horizon, just because it's not mature enough yet, is the mostly solid-state category, which we'll keep on monitoring. And we will also, for all of these, by the way, show updates as well on the website, and we'll keep track of how everything is progressing. So then, in terms of what we would recommend you do if you're not already. So in LFP addressable standard range, cold weather, low cost, fleet, short range segments, we would already start running sodium ion pilots where you can. We would start looking at suppliers by chemistry route, not necessarily by company. In particular for EVs, the layered oxides and hard carbon anodes are particularly important, where we think that especially the hard carbon anodes are going to be a strategic bottleneck, because producing them properly is quite high tech, and looking for a dedicated supply and even building optionality when it comes to procuring enough of it. Right now there probably still is a chance that you can. If you wait too long, this will become a very competitive segment. Then if you insist on keeping going with LFP for now, then LMFP, M3P is a natural next step. It will probably keep it competitive for some time, but if you are not taking sodium ion seriously, we think you will have a problem in the not too distant future. Then finally, before we can open it up for questions and some discussion, if you have any follow-up questions like Tim, please let us know, because for all of those that have been so kind to join us today on this webinar, we will offer you what we call a deep dive for free. So if you have any follow-up questions on any of the technologies that you see in either today's presentation or in the full report that is on our website, and you want to know more, you can let us know, and we'll dig into it and we'll show you exactly what we found. Then final point to note is that today you saw what we can do for basically building technology strategy radars when it comes to battery chemistries, in particular for EVs, but we can do this for anything. So as long as you have a strategic technology question where you want to understand, what does the landscape look like, how fast are these technologies improving, how mature are they, and what does it mean for the future of my business, and in particular, if you want to monitor how that evolves over time, please reach out to us and we can show you what we can do. Thank you very much.
We did collect a couple of questions beforehand, so maybe we can address those while waiting if the live audience has any question in the meantime. Would you like to take the question now, Jard?
Yeah, sure.
Okay. So one of the questions that we received is, most real battery innovation, especially chemistry and manufacturing, is kept as trade secret. Doesn't patent data miss the actual breakthrough?
Well, I would highly doubt that most of it is kept as a trade secret, although of course some of it's kept as trade secrets. But for our methodology, it doesn't really matter, because basically in the end it's a statistical method, and we don't need to measure every single innovation that is out there to get a coherent signal. As long as what is patented is a fair representation of the state of the art of the technology, and some companies will decide to patent and some will not. Based on whatever is patented, we can get a very reliable reading of the improvement rates.
We also have a live question from Debbie. Are there any examples where technology with a high improvement rate did not win in the market?
Well, there are some examples where, for example, regulators decide to ban a technology or to make it very unattractive to go into a certain technology. So, for example, one that comes to mind is if you landscape how coal energy power plants are improving. In Europe and in the US, there's very little improvement. But if you landscape purely for what's happening in China, where the regime is still much more favorable when it comes to coal energy generation, there the improvement rate is much higher. So on average, coal still shows a fairly competitive rate of improvement, but because regulators in Western countries have decided against it, more or less, it does not win in the market here. So just because a technology has a high rate of improvement doesn't necessarily guarantee that it will win, because there's other forces at play that don't have anything to do with whether the technology is any good or not. So in cases where there is a real risk that regulators will change their mind or will go against something, the highest improver doesn't necessarily win. The same is true for pharma. So just because the technology looks good doesn't mean that based on the rate of improvement we can predict how a pharmaceutical compound will interact with a biological system, and it may then still fail in a phase 3 clinical trial, for example.
Another question is, how high of an improvement rate is a clear indicator that a technology will be important? What other information should be looked at in conjunction with improvement rate?
Yeah, so the most important is how it ranks up against its competition. So there's not a certain rate that will tell you that the technology is improving fast or not, because it's always relative. So, for example, if we go back to this slide, right, so it's not that 80% here is a significant number, because it depends on what you're comparing it to. And always technologies that serve a similar purpose will have a relatively similar rate of improvement. So if we would also put large language models on this chart, then all the battery technologies would almost disappear into nothing, because large language models are improving much, much, much faster than any battery chemistry ever could. But that doesn't mean that sodium-ion, in this case, doesn't have a high rate of improvement, because sodium-ion batteries and large language models are not competing. They serve completely different purposes. So basically, if you find that a technology that is competing with another technology has a high rate of improvement, comparatively speaking, that's when we start concluding that this is going to be the future of a particular technological area.
Another question is, can you take political influence into account, such as a negative assessment of heat pumps compared to gas heating systems in Germany?
Yeah, that's also interesting, because with a lot of the backwards looking studies that we've done, for example, even when it comes to the battery space, initially, regulators were not very excited about batteries, because they're heavy, they weren't very energy dense in the beginning, they would catch on fire, which is still, in some cases, a bit of an issue, although much less so. And in fact, the regulators seemed to heavily favor hydrogen, because there was an enormous amount of subsidies going in that direction, an enormous amount of backing, and also the corporations themselves predominantly invested in hydrogen over battery technologies. But nevertheless, batteries improved a lot faster, and now we have batteries everywhere, and increasingly so. And you can also see that the regulators' posture changes because of that. So more often than not, the political favoring or disfavoring of a technology lags its improvement rate. So what we find pretty frequently is that if a technology is just improving much faster, at some point it will become undeniable, which is also the case with heat pumps, which is something that we've looked at in the past. If you look at heat pumps compared to gas heating, heat pumps are improving significantly faster than gas boilers or heaters. So even though today, on the face of it, heat pumps are not in all cases super competitive or have some downsides compared to gas heating, they are improving a lot faster, and therefore I would say it's highly likely that also in the future the political posture will adapt. I see we have another question earlier from Tim. If we have any comment on neutron experience, I'm not sure what you mean, Tim. Can you clarify?
Maybe while we wait, another question that we have is, patents are a lagging indicator. Won't that affect the results?
Yeah, that's true. So patents are a lagging indicator if you look at the actual patent itself. As far as we know, looking at these patterns in citation data, so in particular cycle time and knowledge flow, is the only leading indicator that we've been able to find when it comes to patents. Because although if we look currently at the latest published sodium-ion or LFP or NMC patents, you'll never see the actual state of the art because those patents aren't yet published, right, because of the publication lag. These patterns that precede the rate of progress will show up in the citation networks really early. So for large language models, for example, even though ChatGPT was launched in 2022, and I think by now it's pretty undeniable that large language models are having a significant impact on the world. In 2017 would have been the first year in which we would have been able to show an exponential increase in the rate of improvement for large language models. So the actual patent filings are a lagging indicator, but if you go one layer deeper into the citation networks, then you can actually find leading indicators.
So Tim answered. Natron was a company who tried to industrialize prison-based sodium batteries in USA, but they failed beginning of 2026.
I haven't looked into this in detail, but we can make that one of the deep dives. Happy to follow up with you on that. We can maybe do a quick scan to see how they compare to some of the others in that field.
Another question is, can you tell us more about the ignition temperature in case of overheating, or if you have nail penetration?
Yes, that we can also do in a deep dive, absolutely. So we'll follow up with you, Ulrich, and you will not get our opinion, but you'll get facts. Any final questions? All right, then thank you so much for joining. Really appreciate all of you showing up for our webinar. We'll make sure to share the slides with you guys and also the recording. And then for those of you that asked us questions to dig into a bit more, we'll dig into it and we'll reach out to you with the results. Thank you very much. Tim. You're welcome.
Do you think will it be possible to create such value chain, for instance, in Europe instead of China?
I mean, anything's possible, but based on if you look at the patent filings, like 94% of it is in China, and they're way ahead of anyone else, which is also why in the end I would suspect would be one of the main reasons why Natron went under, but we have to dig into that a bit more. Yeah, almost all of the battery-related innovation is coming from China. Whether it's on material processing, any component in a battery, manufacturing technology associated therewith, and also even if they wouldn't be winning on the frontier of the technology, they have a massive manufacturing base, and they're way, way, way ahead. And so I think it'll be increasingly difficult to compete with what the Chinese have already built. All right. Thanks again.
Thank you.
Hopefully, we'll be in touch. Thank you so much. Have a very nice rest of your day.
Thank you. Bye.
Bye-bye.